Welcome to MEI Mechanics. We're on the topic of forces and moments, and this is video 1.5, sliding and toppling. So when we're thinking about equilibrium of rigid body on a rough surface, we need to realise that this equilibrium could be broken in two different ways. So imagine the situation is as shown in this diagram. So we have a box resting on some rough surface, and we're applying a force here right at the top of the box, in this case acting to the left. Well, what could happen? Well, it may be that it slides. That would happen if the coefficient of friction was low. So imagine that was a block of ice or something, or resting on an ice rink. If you give it a push, even a slight push, it's just going to slide along. It's going to be difficult to make it topple over. But if the surface is rougher, got a high coefficient of friction, then it's not going to want to slide as well, and it may be that you end up pushing it so hard that it topples over. So what we're going to be thinking about in this video is, at least firstly, can we work out which of these things is going to happen in a given situation? So here's the first example then. We've got a box with a mass of 10 kilograms. It's resting on rough ground, and the coefficient of friction is 0.3. Alright, and the height of the box is 1.5 meters, width is 0.8 meters, and we're applying an unknown force to the box as shown, but it's acting to the left. And this question's in two parts. Firstly, we're going to find the value of P that would cause the box to slide, and then we're going to find the value P that would cause the box to topple. So obviously in reality only one of these things can happen, so when we're considering each separate case we'll have to assume that the other one hasn't already happened. Okay, so conceptually that might be a little bit tricky, but let's just see how this works and hopefully it'll make sense in the end. So for part A then, we want to find the value P that will cause the box to slide. So that means that we're assuming that the box is not going to topple. So we're not going to worry about moments or anything like that. We'll do that in part B. We're just going to assume that it does slide and work out the value P that will cause that to happen. So what other forces do we need to consider? Well, obviously there's going to be the weight of the box. It's 10 kilograms, so the weight will be 10g. And there will then be a normal reaction force. It's acting from the ground, but I'm going to place it here on this diagram because we're not going to think about moments yet, and that will be R, and there will be friction acting on the box here, acting to oppose the push. Alright, and if it's about to slide, then that friction will have its maximum value. So firstly, resolving in the vertical direction, we have R acting upwards and 10g acting downwards, and it's not going to be accelerating in a vertical direction at any point, so that will have to be 0, and so that means that R is equal to the weight of 10g. Then horizontally we have the friction acting to the right, and we have P acting to the left, and again if it's just on the point of sliding then it won't actually be accelerating, so I can say that equals 0, and so P will equal F, but because we're thinking about this being on the point of sliding, that would be F max. It will be equal to mu R, and we're told that the coefficient of friction is 0.3. The reaction force is 10g, we've worked that out. So we end up with a value of P equal 0.3 times 10 times 9.8, which is 29.4 newtons. So on the part B, now this time we want to find the value P that would cause the box to topple. So this time we're still told there's coefficient of friction 0.3, but we're going to have to kind of ignore that. We're going to have to assume for now that the coefficient of friction is high enough that the box is not going to slide before it topples. So if we imagine what happens if it's going to topple, how's that going to happen? Well, if I'm pushing it that way, then it's going to be toppling like that, isn't it? And so it will be rotating about that point there. That point will remain fixed in its position. So if we take moments about that point, then that would be a sensible thing to do. Why is that? Well, it's because the frictional force which would have to be acting at that point, because that's going to be the only point in contact with the ground if it's starting to topple. And that means that the friction will have 0 moment about that point. Okay, so that's the point we're going to use. So why don't we label that point X, and we can see there's a frictional force acting at that point. Now when it comes to the normal reaction force, we need to be careful as well. Again, just like with the friction, if this thing is going to be toppling, that point's the only point in contact with the ground, the normal reaction force will also be acting from this point of contact. So it will look like that. So neither of these will have any moment about X. But there is one other force acting, of course, which is the weight. Now I've placed that on the centre of mass of the shape. It's 10g. And what we're going to be interested in is its perpendicular distance from that point, which will be half the width of the shape. Okay, so that distance there, half the width, that will be 0.4 meters. Okay, and of course the other thing which is going to be important is going to be the perpendicular distance of this force here from that point. So if I think about that, that's perpendicular distance is the height of the box, which is 1.5. So let's take anti-clockwise moments about point X. We have P with a perpendicular distance of 1.5. That's acting anti-clockwise. And then the only other force which is going to have any moment about X is this 10g, and that's acting clockwise. So we have minus 10g times its perpendicular distance, which was 0.4. So if I rearrange that for P using g equals 9.8, I find that P in this case is equal to 26.1 newtons. So let's have a look at both of these results then. So the force that would cause the box to slide is 29.4 newtons. The value that will cause it to topple will be 26.1. So what that means is, if I start to push the box, so start with a force which is 0 and just gradually increase that force, it's going to reach the value of 26.1 before it reaches a value of 29.4. So it's going to topple before it can slide. Alright, so that's what we can conclude, is that the box will topple. Now in this second example, we're also thinking about the idea of toppling. But this time we've got this object is on a slope with an angle theta to the horizontal. Alright, it's the same dimensions of box as earlier, but we're told to assume that the box does not slide. So we're assuming that this surface is rough enough that the box isn't going to slide. Can we find the value of theta such that the box is on the point of toppling? Now, there's quite a clever way of doing this. If you think about it, again, it's going to be, if it does topple, then it would be toppling about that point there. So we would be thinking possibly about moments about that point. But there's going to be a critical point, and it's when it's just on the point of toppling, where that moment would have to be 0 and just about to become a clockwise moment that's trying to turn it to topple. And at that point, the centre of mass of the box will be directly above that point where it would topple. Okay, and what that means is that all the forces that I would want to draw on this box, so maybe friction or normal reaction at this point, or the weight acting here, none of them have any moment. So that is the point at which it's going to be on the verge of toppling. So all I need to do, I don't even need to draw any forces, all I need to do is work out that angle, the angle at which the centre of mass will be directly above the point of contact. Alright, now where is that angle? Can I find this angle on my shape? Well, yes, and probably the most easy way to see it is if I think about something like this. That angle here will be equal to that angle here, and I know that that shape has a width of 0.8 meters and a height of 1.5 meters. So I know that tan of theta is 0.8 over 1.5. Take the inverse tan of that, and we find that theta is equal to 28.1 degrees. So that concludes video 1.5, sliding and toppling, and concludes the topic of forces and moments.